So next thing, so to make things simple, I used the word message, like referring to the data, but in the CAN interface, we don't use a message like as a technical term. Instead, we have a frame. So frame has defined structure, has defined elements, and within that we have this real payload, real data. So next thing, I'm going to present the frame format. So whenever the node transmits data, it has to follow, it has to comply with this format. And of course, when you use the microcontroller, if it has the CAN peripheral, so at the hardware level, everything is implemented. You basically need to ask the CAN peripheral to send this data, and it will structure everything as you defined. Okay, so no worries about that. But to understand in general how the CAN operates, I think it's really crucial to understand every part of the frame format. So next, let's briefly go through the different parts of the frame. So first we have SOF, that we call start of frame. So it is always dominant, meaning that its value is always 0. Then we have the identifier that we already discussed. So I used the name ID instead of it, but identifier it is when we have the arbitration. So it's an 11-bit identifier for arbitration. Then we have another bit that we call remote transmission request. So here, if it is value is 0, it means that the frame contains real data. If it's 1, it means that it is requesting data from the other node. Okay. Then we have IDE, identifier extension, that I will explain a bit later. R0 is reserved. Then we have DLC, data length code. It is always 3 bits, and it defines the data length. Okay, so we have the data which could be maximum 8 bytes. Then we have standard, I think, elements like CRC, cyclic redundancy check, acknowledgement, end of frame, and then so on. There's nothing much to say. So this is the classical CAN frame format. But as I said you before, the CAN interface was designed in 1980s, 1990s. So at that time, I guess 11-bit was enough for the arbitration, but all the technology has been becoming more and more complex. So I guess 11-bit was not enough. So that's why later extended CAN was introduced. So in extended CAN, the frame format looks like this. So it's almost identical to the standard CAN frame format, but here we have not 11 but 29 bits for the arbitration process. So more nodes, more messages can be sent. Basically, you have more choices to define the ID of the frames. So this is the only difference, I think, compared to the classical CAN. So as I said you before, we have this ID. So this bit is necessary to define the standard classical frame format and extended CAN frame format. So if its value is 0, it means that standard. If it's 1, is extended. So the interesting thing about the CAN is that it's a backward compatible. So the frame with the classical frame format and the messages with the extended frame format can live within the same bus, can function within the same bus with no problem, because we have this ID which defines the frame format. So if its value is 0, it means that it's a standard. So meaning that classical CAN frame format has higher priority than the extended CAN frame format. So this is how it basically works. Classical CAN worked great for a long time. It helped to solve different problems in various domains, and but as systems has been becoming more complex and smarter, two main problems showed up. The first is the small payload. So as I introduced you before, one frame can contain only 8 bytes, and but modern applications, you need much more data. So this is the first problem. The second, a fixed bit rate. So the arbitration and the data use the same speed. So it was typically less than 1 megabits per second. And this is becoming too slow for high bandwidth systems. So to solve these problems, flexible data rate, FDCAN, has been introduced. So it has, I think, two major differences compared to the classical CAN. The first is the larger payload. So instead of 8 bytes, we have maximum 24 bytes. So 8 times greater than compared to the payload in the classical CAN frame. So this is the first main difference. Second is the bitrate switching. So during the arbitration, you have a slow data rate. And then when we have the data built, it can switch to the much higher speed. So it can switch to 8 megabits per second. And you might ask why we cannot use higher bitrate during the arbitration. The problem is that during the arbitration, as I said, multiple nodes can send the data, can send the IDE. So if you use a higher bitrate, you may end up with undesired, let's say, state of the data line. That's why during the arbitration we have to be really careful, so the CAN uses the low bit rate. But once we switch to sending the data, we have only a single node which is sending the data, so we can use higher bit rate. So that's why in flexible data rate we have bit rate switching. Again, let's check the frame format in FDCAN, flexible data rate CAN. So here we have a few more additional fields. First, flexible data format. So it is always 1 in the CAN FD. Then we have another BRS, bitrate switch. So if its value is 0, then the CAN uses the same bitrate. But if we have 1 recessive, it means that the data is sent at higher bitrate. Then we have error state indicator. I think it's not so relevant. So this is how basically the CAN interface has evolved. And next thing, I'm going to explain another really important important feature in the CAN interface that we call CAN filtering.